Thank you very much. Thank you for this kind introduction. Also, many thanks for having me here. I'm very happy that I can present our work with the Zhu sisters, so Ronxian and Qianqian Zhu. They're twin sisters. They are now in Beijing, but they are also partly affiliated to Bielefeld University, where I belong to. And we started this project about 1.5 years ago, where I attended a mini course given in the Czech Republic by Vlad Vikol on non-uniqueness for Navier-Stokes equations. And I became really excited about this. And since I come from the SPDE community, so I like to work on stochastic partial differential equations rather than deterministic ones, I was interested in the question what can be said about the stochastic Navier-Stokes system. And I will also explain to you why we are motivated to look at this system under some stochastic perturbations. There are different reasons one may want to consider that. But one of the reasons was actually that some noise can help us with the uniqueness issue for the deterministic Navier-Stokes system. And so we started working on this question together with the Zhu sisters. And in the end, the result that we obtained is non-uniqueness in law. So I will explain to you everything much more in detail. But let me start slowly. So probably you all know what the Navier-Stokes equations are for. So they're equations that come from physics, and they describe a flow of a fluid, a flow of an incompressible fluid. So I'm interested here in incompressible Navier-Stokes equations. In particular, they describe the time evolution of the velocity of a fluid. And let us now stop for a moment and think about this little example that I have here. Yeah, so you take a glass of water, you put it on your table, and now the Navier-Stokes equations tell you how the flow of this water is going to evolve in time. But as you see on the picture, at the beginning of the time, so let's say at time 0, nothing is moving. And then if I ask you, well, what do you think will happen overnight, or when you go away, or when you just look at the water? Of course, you all tell me, well, nothing will happen, right? It just stays there. And unless I stir the fluid or shake it or do something, I don't expect anything to happen. Okay, and I of course agree with you, but yet there was this very remarkable paper of Tristan Buckmaster and Vlad Vikol, where they proved that there are weak solutions to the Navier-Stokes system, which are compactly supported in time. Yeah, now that's a mathematical notion, compactly supported in time, but what does that mean on this picture? Well, that means that the flow starts off from 0 at time 0, meaning the velocity is 0 and nothing is moving. And then the solution or the flow becomes non-trivial. So suddenly things become moving without any external force. And then after some time, things again calm down and the velocity becomes 0 again. Yeah, so of course we think this is totally crazy and this is not physical, but purely mathematically, such solutions exist to the Navier-Stokes equations. And of course, the big open question is, we would like to somehow say these solutions do not make any sense, right? And here in this example, it is easy to decide that, okay, this solution is really not physical and we just throw it away. But for other solutions, it's not so easy to decide what is physical, what is not physical, and how to choose the correct solution. Okay. So this was somehow the starting point of our analysis. Now I would like to be a little bit more precise about the Navier-Stokes equations and then tell you what motivation I have to put there some noise. Yeah, so here we have some mathematical formula. Probably you have seen it before. So U for me is the velocity, and this is the Navier-Stokes system. So you see we study time evolution of the velocity. We have the so-called convective term here on the left-hand side, and this is the real troublemaker for this system. Yeah, this is where all these interesting phenomena come from, because it is a quadratic nonlinearity. Okay, we have some dissipation term on the right-hand side, so Laplacian of U, and mu is a positive viscosity constant here. I have also included here some external forcing that could be like some stirring of the fluid, or eventually we would like to take it stochastic. Yeah, we have also the second equation, which comes from the conservation of mass. So this is the incompressibility constraint for the velocity. And I would like to just, for simplicity, look on this equation with periodic boundary conditions. So I'm on the 3-dimensional torus and in some finite time horizon. Okay, what I haven't mentioned is that there is also this P on the left-hand side. This is gradient of the pressure. And this becomes basically a Lagrange multiplier, which you need because you have the second constraint for your velocity. Okay, and so these equations were given to us mathematicians by physicists. And from our side, what we want to understand is, do solutions even exist? Are they unique? Can we understand how they behave if the time becomes very large? So these are the questions that we are interested in. Just to summarize briefly, probably you also know that existence of strong solutions. So strong solutions here means really solutions that are smooth. Yeah, so the derivatives that you see in the system, they exist really in the classical sense. We know that these solutions exist locally in time, sorry, but their global existence, this is included in one of the Millennium Prize problems. So strong solutions exist locally in time and they are unique. Because they are more regular, we can prove uniqueness. Okay, but it's not very nice for studying the system in the long run if a solution exists only on some very short time interval, right? And therefore, we want to find a different notion of solution, which is more suitable for studying the system in the long run. And one possible notion is given by weak solutions. This basically means that I look at these derivatives that appear in the system as distributional derivatives. And I consider this Navier-Stokes system as system in the sense of distributions. And now existence, global in time existence for these solutions becomes significantly easier. So this can be proved. However, the question is now uniqueness. And actually, as it was shown by Buckmaster-Vicol, these solutions are not unique. They showed it on the example on the previous slide for the 0 initial condition, at least if we think of the forcing being 0, but it could be extended to other initial conditions as well. Also, there is like this issue that for strong solutions, we don't have global existence, but we have uniqueness. For weak solutions, we have global existence, but we don't have uniqueness. Okay, and so, sorry. So the question is, what can be done with that? But before I get there, let me be more precise about the results of Tristan Buckmaster and Vlad-Vicol. So in the paper I mentioned on the second slide, they proved that for every given non-negative smooth function, this should represent the kinetic energy. And you see it is bigger equal than 0. There exists a weak solution to the Navier-Stokes system, which has this prescribed energy for all times. And now you see how these solutions compactly supported in time actually come in. You start off from energy being 0 at 0, then it becomes non-zero, and then it becomes 0 later again. So this is remarkable to say at least a little bit, but it's really somehow it doesn't fit to the physical picture we have about these equations. And as I mentioned, this already proves non-uniqueness of weak solutions for the 0 initial condition. To extend it to other initial conditions, one could look at the paper Buckmaster-Colombo-Vicol. This was actually a subsequent work. So this is the archive year and this is the published year. And here they have a very nice result on connection of 2 strong solutions. So you take two solutions. They are strong, that's important. So they are regular and they solve the system on some time interval. And now what you want to do is you want to take the first third of your time interval and find a solution which is equal to the first strong solution there. And then on the last third of your time interval, it should be equal to the second solution. So basically you take two strong solutions and you want to connect them by a solution. So this cannot be done by a strong solution, but they were able to connect them by a weak solution. Yeah, so altogether there is a solution U which solves also the system on 0 capital T. And on the first third of the interval, it is equal to the first strong solution. And on the second, in the middle, it does something. And at the end of the interval, it is equal to the second strong solution. Okay, and so now you see this already proves non-uniqueness for many initial conditions, in particular for every initial condition, which gives rise to a strong solution. Okay. And so both these works relied on the method of convex integration, which was brought to fluid dynamics by Deleuze-Székely, who started that for the Euler equations, and then it led really to an avalanche of results, eventually solving the Onsager conjecture by this group of authors whose names are on the slides and others. And this is also the method that we then applied to the stochastic system, but I will get to that. Yeah, so what these results that, yeah.
Hi, Martina, it's nice to hear you. I'm so sorry to interrupt, but I have a question about, maybe I missed something where I was distracted, but this construction you mentioned by a Bookmaster Colombo vehicle. So does it necessarily happen that at some point between T/3 and 2T/3, the solution disappears, or possibly something else happens? Like, does it? So it has some prescribed behavior between 0 and T/3, some other one between 2T/3 and T, and does it disappear somewhere in the middle, or not necessarily, with their construction, or not necessarily?
By disappear, you mean that it becomes 0?
Vanishes, sorry, vanishes, yes. Does it vanish?
I don't know. I know that there is some, I would say no. They have some other result, which I didn't mention here, somehow estimating the size of the set where the solution is not regular or does not have certain regularity. But yeah, that's all I can say. So I don't think it can disappear or it can be 0.
No, it's just that if I remember well, in the papers by Deleuze and Székely, they built solutions with compact support, but they were like, I guess they were not almost C1/3, they were C1/10 or something like that. That's how I remember it was in the first papers. That's all.
Yeah.
Just by curiosity.
Yeah. Okay. Good. Yeah, I cannot say more. Sorry.
Okay.
Well, you can arrange it this 0 if you want. So it's your choice. You can make it 0 if you want. You can make it 0 at the time T over. Yeah, you can definitely make it.
Oh, yeah. Okay. Yeah. No, I see what you mean. Yes. If you just iterate, yes. Okay, you iterate and you
restrict. You would prescribe the 0 solution.
Yes.
You can prescribe it if you want on sub-into. But I mean, this also shows that there's no weak, strong uniqueness. None of these are very far from the Leray-Hopf solutions.
Exactly.
There's no weak, strong uniqueness principle for any of this.
Yeah, exactly. And I will get to that on the next slide. It somehow boils down to the question also that we had on the second slide, namely that these are somehow not physical solutions. And so the question is, what is actually physical? And to our understanding, at least these Leray-Hopf solutions are somehow much more physical than this. And so this is what I want to explain to you here. So I take my system again, and for simplicity, I take the forcing equals 0. And so the notion of Leray-Hopf solution means it's a weak solution in the sense it solves the system in the sense of distributions, but there is an additional condition, the so-called energy inequality, which it should satisfy. Now, to understand this, if you assume that your solution is smooth, and this is now really an additional assumption, then you can test the equation by the solution itself. And this is precisely what I did here. So the duality here means just the L2 inner product. Yeah, I just multiply everything by U and integrate. Now, if we look at this first term here on the left-hand side, this is 1/2 of the time derivative of the L2 norm square. Due to the divergence-free constraint, the second term vanishes, which is really good for us because as it is quadratic here, so the nonlinearity is quadratic, otherwise we wouldn't have been able to control it. So our only hope to get some global in time estimate is basically that it vanishes or that it has a good sign so that it remains on the left-hand side. Yeah, again, due to the divergence-free constraint, the pressure vanishes. And if I integrate by parts here in this term on the right-hand side, you see that I get a good term on the left-hand side. Yeah, so I get the gradient square on the left-hand side, and I have the so-called energy equality. Yeah, but you remember I said assume the solution is smooth, and we cannot assume it. I mean, we cannot prove that such a solution exists globally in time, but we can do this computation on the level of approximation. Yeah, so for instance, Galerkin approximation, then the solution is smooth. I can do this computation, and I would indeed get energy equality. But then in order to pass to the limit, I don't have enough estimates to pass to the limit in this gradient term. Yeah, and that's why I eventually only can hope for inequality. Yeah, so there would be this inequality if I also integrate in time. And this is what then defines the notion of a Leray solution. And so roughly speaking, it is a weak solution plus this additional inequality. Yeah. And it remains a big open question whether the Leray solutions are unique. So we would like to believe that these are somehow more physical solutions, but the question is whether this additional criterion suffices in order to prove uniqueness, and we don't know that yet. And you also see that the example from my second slide with the glass of water, it cannot satisfy this inequality. So if the energy is compactly supported and non-trivial at some point, it wouldn't satisfy the energy inequality. Okay, let me now move on to some stochastic perturbations. So as I said, people had many motivations why they believed some noise in the Navier-Stokes equations could be good. And there are motivations coming from physics. There are also motivations coming from mathematicians somehow hoping to prove better results. Yeah, so the noise that I consider is in the so-called Ito form. W is a Brownian motion, and I have there some coefficient G and possibly also dependence on the solution. Yeah, so I don't know if you are familiar with this notation. Basically, I can divide by this dt here, and then you see here on the left-hand side, I would get the time derivative, and here I would get time derivative of the Brownian motion. Yeah, but Brownian motion is not differentiable because it has very rough trajectories. That's why we use rather this somehow stochastic notation, and this stochastic integral is in the sense of Ito. Okay, and so I said one motivation comes from physics, namely from turbulence theory. One may find in several physics papers that in a sense, some noise could model the boundary effects that create turbulence. I put here a question mark. So this is somehow accepted that some kind of additive noise, meaning it does not depend on the solution, it is supported only on the large scales, that it should be a good model for some turbulent behavior. But by far, this is really true. How much it is or it is not a good model, to my knowledge, this is still somehow with a question mark. But it is well accepted also in the SPDE community, and I believe that people use this model. There are also motivations more from the mathematical side. Namely, there was a hope that some noise could help with this well-postedness issue. And actually, there are some examples, even for the Navier-Stokes system, where stochastic equation behaves better than a deterministic one. So this goes into the direction of regularization by noise. One example of such a good noise, but again, there are doubts in to what extent this is a physical noise, is such a damping noise. So if my coefficient G of U is just some constant alpha times U, so linear in the solution, then it was proved by Reckner's Who's Who that there is no explosion with large probability. So the strong solutions do not explode with large probability. And this is really somehow how large is determined by this parameter alpha. And basically this noise gives you some kind of damping. And if you try to do the energy estimate, some of the computation from the previous slide for this noise, you will see immediately why this has hope to help you, because you get from this, you get one good term on the left-hand side of the estimate. So it has some kind of stabilizing effect. Okay, a noise that may be somewhat more physical is a transport equation. And then Flandoli-Luo proved there is no explosion for the vorticity form, again with large probability. Here the noise should look like this. So sigma is some vector field and there is gradient of U. And here this little circle denotes a Stratonovich stochastic integral. So this is a different kind of stochastic integral. And actually, I'm not being entirely honest with you. Here, they need to look at the vorticity formulation. So U here shouldn't be the velocity, but vorticity. And that's indeed very, then the noise becomes, again, less physical. So it's like you first write down the vorticity formulation, and then you add such a transport noise. And then they can prove that there is no explosion of the vorticity with large probability. I find this very remarkable, although there is this criticism that the noise is not very physical. But still it is remarkable because the reason why it works is they are able to transform such a noise to an artificial viscosity. So there is a scaling argument and they converge to a limit where the limiting system has more viscosity than the original one. And it's a deterministic Navier-Stokes in the vorticity formulation. And since the viscosity is larger and the lifespan of the solution depends on the size of the viscosity, you become automatically a longer lifespan of your solution. And this is precisely what they use here. Yeah.
So may I ask a question or a comment? May I do a comment?
Yeah, of course.
Yes, so physically speaking, if you want to reproduce the physics of the cascade of energy of Kolmogorov thing generating older 1/3 solution, the forcing, it has to be smooth in space because you put the energy at large scale and it will be damped at small scale. So you don't want a Brownian motion, but more something smooth and maybe delta correlated in time. But if you use a delta correlated in space force, that's physically speaking a bit weird.
Yes, I agree with you. And this is not what is meant on this slide.
Okay.
Because if you really wanted to have space-time white noise here in 3 dimensions, you need to use regularity structures and you get local in-time solutions.
Exactly.
So thank you for this remark. I didn't say this. There could be a spatial dependence either here in the coefficient G. We usually put it in the coefficient G and think of Brownian motion, just time Brownian motion. But the spatial dependence has to be smooth indeed. Yeah, and actually by this example of modeling of turbulence, it should, the noise should be independent of the solution and really only supported maybe on a few Fourier modes. So it should be really like even compactly supported in Fourier.
Great, that's great, perfect. Thank you very much.
Yeah, thank you for the comment. Yeah, so this is one reason why people were hoping, yeah, okay, maybe stochastic equations could somehow be useful here. Another reason is the issue of uniqueness. Because for SPDEs and SDEs, we have two different notions of uniqueness. There is pathwise uniqueness and there is uniqueness in law. Pathwise uniqueness means I want to compare two solutions that live on the same probability space and they have the same initial condition. And now the statement is they're pathwise unique if the probability that they are the same for all times is equal to 1. So really pathwise, meaning I take almost every omega, that's my randomness parameter, and the two solutions should coincide. So this is pathwise uniqueness. And the second notion is uniqueness in law. And here I want to proceed differently. I don't care whether these two solutions are defined on the same probability space. They could be defined on different spaces. And I want to only compare their probability laws. So the push forward measure generated by these solutions on the space of trajectories. So when they start from the same initial law, the uniqueness in law then tells me that the law of one solution is the same as the law of the other solution. And now the point is that pathwise uniqueness has somehow very similar difficulties to the uniqueness in the deterministic setting. Uniqueness in law, on the other hand, is a weaker notion of solution. You can see that if two solutions are pathwise, if they are uniquely pathwise, if they coincide pathwise, then they have the same law. So uniqueness in law is a weaker notion of uniqueness. And therefore, one could, first of all, hope that maybe we don't know how to prove pathwise uniqueness. Maybe that's too difficult, but maybe uniqueness in law can be easier to prove. Actually, I will show you on the next slide, there are examples of equations where pathwise uniqueness does not hold and uniqueness in law is true. Okay, and there is also the so-called Yamada-Watanabe-Engelbert's theorem, which tells us the following. For a certain class of SDEs or SPDEs, the following are equivalent. On the one hand, I have pathwise uniqueness. On the other hand, I have uniqueness in law and existence of a pathwise solution. Okay, so I should explain, what does a pathwise solution mean? So this means that I solve my system, my stochastic system, on a given probability space, and the solution is adapted to the given Brownian motion. And for instance, if we proceed by a compactness argument, we don't get it. And as you know, for Leray solutions for the Navier-Stokes system, up to recently, the available existent results relied really on this compactness argument, which means for SPDEs, we were never able to prove existence of pathwise solutions. And actually, we are not able to prove existence of such solutions up to now, on a given time interval. We have only a partial result, which I will mention later. Okay, and so you see, if you believe that uniqueness in law is easier to prove than pathwise uniqueness, then you may think, okay, then I prove uniqueness in law, and then I prove existence of a pathwise solution. And from this Yamada-Watanabe-Engelbert's theorem, I actually obtain pathwise uniqueness, which would bring me closer to the deterministic uniqueness. And this was, one could see hints of this in the literature, that this was what people were somehow hoping to do. How to approach the uniqueness issue coming from SPDEs via this trick. Okay, now, so there are other positive examples why noise helps. Here I have an example where the deterministic equation does not have a uniqueness, but if I add noise, then I have uniqueness in law. And actually, it's a very simple problem. So just such an ODE where on the right-hand side, I have modulus of x to some power alpha. And the point is that I start from the initial condition equal to 0. Now you see, depending on this parameter alpha, I get different behavior of my solutions. So first of all, if alpha is bigger or equal to 1, the nonlinearity is local Lipschitz, and therefore there is a unique solution which is just 0. However, if alpha is between 0 and 1, I get infinitely many solutions. So I can start off from 0 and I remain 0 up to some chosen time s, and then the solution becomes non-zero. And so you see, parameterized by the time s, where I leave 0, I have infinitely many solutions. But on the other hand, if I add such a stochastic perturbation, so it's a Brownian motion in time, it's additive in the sense it does not depend on the solution x, and this equation can be proved to be unique in law by Girsanov's theorem. So this is also what one would like to hope to do for the Navier-Stokes system, but of course we know Navier-Stokes system is much more complicated than such a very simple ODE. So it's just to give you hints why maybe from the mathematical reasoning you may want to include some noise. And there are more reasons, because certain regularization by noise can also be observed when you study long time behavior of solutions. So for instance, here, if I look at such a stochastic differential equation, so I have some metrics here, Q, and now I want to study really the long time behavior. So I define U at time t and position x, where little x here is my initial condition for the SDE. And I define this as an expectation of some test function phi evaluated at xtx. And xtx is a solution to this SDE at time t, starting from the initial condition x. Yeah, and to study basically the behavior of the law of such a solution, I can study this function u. And if you do the computation, so you compute the time derivative of this right-hand side, you come up with the so-called Kolmogorov equation. So this function u solves such a parabolic equation that we see here. Okay, the question is whether or not the equation is indeed parabolic. Yeah, but at least formally, we get this Kolmogorov equation. And the initial condition is now given by this test function phi. And now you see immediately that, well, this could be a parabolic equation, or it does not have to be a parabolic equation, or it could be parabolic degenerate. And it all depends on this matrix Q here. Yeah, and so for instance, if you think of Q being the identity, then you get 1/2 of the Laplacian here. Yeah, so now you have a nice heat equation with some transport term. And this has very nice properties. In particular, there is smoothing with respect to this parameter x here, with respect to the x variable, which originally was my initial condition in the SDE. Yeah, so basically what a non-degenerate noise does here is it gives you smoothing of the law of the solution x here with respect to the initial condition. And this is something which is used in order to prove strong Feller property and to deduce then uniqueness of invariant measures. Yeah, so this is how non-degenerate noise helps with uniqueness of invariant measures. You also see a reason or a hint of a reason why it is actually difficult to prove uniqueness of invariant measures if the noise is degenerate. And we said that for this model of turbulence theory, the noise should be very degenerate, actually supported only on few Fourier modes. Yeah, because we see, well, for instance, if the other extreme comes in, meaning the matrix Q is 0, meaning I have just a deterministic ODE, then this term is no longer there, and I have a transport equation, and I cannot expect any smoothing with respect to the variable x. Yeah, so then I get the so-called Liouville equation, and there is no smoothing. So here you see really how non-degenerate noise can help you. And of course, this was somehow a finite dimensional SDE, The problem or difficulty in applying somehow these ideas to the Navier-Stokes system is that then this variable x is not RD valued anymore. It would be infinite dimensional, taking values in L2. And then everything becomes much more complicated because it becomes somehow parabolic or possibly degenerate parabolic equation on infinite dimensional spaces. But still, somehow this intuitive idea could be used by the Prato-Debush for the stochastic 3D Navier-Stokes equations with non-degenerate noise. Yeah, so the non-degeneracy means that the Kolmogorov equation is really an honest parabolic equation. And they were able to prove that there is a transition semigroup and there is a unique ergodic invariant measure. And so this was in 2003. And yeah, also in this paper, one finds the sentence saying that uniqueness in law may be easier to prove than pathwise uniqueness, but it remains open. And this brings me finally to our result on non-uniqueness in law. Let me just say right at this point that we didn't prove these people wrong because they're always thinking in the setting of Leray solutions. Yeah, and exactly as it was the case for Buckmaster-Vicol, our solutions where we prove non-uniqueness in law, they're not Leray solutions. So they're weak solutions, but they do not satisfy the energy inequality. Okay, yeah. So now I arrived to our result. So we consider the stochastic Navier-Stokes system with a stochastic perturbation as we saw it before, but we restrict ourselves to two very particular cases. First of all, we consider the additive noise, meaning there is no dependence on the solution, and then linear multiplicative noise, where the dependence is just linear in the solution. The reason for this is that it permits us to make a certain transformation. We don't have to deal with the Ito integral here. We can transform this SPDE into a PDE with random coefficients. And then we can basically apply the machinery of Buckmaster-Vicol pathwise by fixing for every fixed randomness parameter omega. That's somehow the first idea. Yeah, so in the first step, we do really this transformation and we apply convex integration as in Buckmaster-Vicol. Now, what is remarkable here and what is actually also necessary for the non-uniqueness in law is that the solutions that we construct by convex integration, they're probabilistically strong. So on one of the previous slides, I named them pathwise solutions. So this is not what you get by compactness argument. By here, we do not rely on a compactness argument. Here we rely on a direct iterative procedure and direct construction. And therefore, we are able to prove that these solutions are probabilistically strong. On the other hand, they are analytically weak, and that's the same for Buckmaster-Vicol. We can only do so up to a stopping time. Yeah, and this is somehow, I think this is still not a nice thing about this approach, and we are trying to get rid of this restriction on the stopping times. What we do with that, it's we basically control the noise. Yeah, basically I introduce a stopping time, which just tells me, I mean, whenever Brownian motion hits some level, I stop the time basically. And therefore I have a uniform in omega control for my noise. And therefore I'm able to apply the convex integration somehow really pathwise. And this also relates to the issue that I raised a few slides ago when I said that till now I don't know how to prove existence of globally defined probabilistically strong solutions. So I can do it here only up to a stopping time. Yeah, and in order to prove non-uniqueness, we want to force these convex integration solutions to behave badly. And how badly? Basically, we can force them to increase the energy. That's also similar to Buckmaster. We call, we do kind of a simplified version, which they have in lecture notes, not in the paper. Yeah, so these convex integration solutions, they behave badly and they increase energy. But the problem is they are only defined up to the stopping time. And so, okay, from here, I can already prove some kind of non-uniqueness up to a stopping time, but we wouldn't find this very satisfactory. That's why we wanted to extend these solutions to the whole interval 0 infinity. So first they are defined on some random time interval, and then we wanted to continue them somehow. We were not able to continue them by convex integration because somehow the initial condition comes in a construction. It's not something that we prescribed there. But what we could do is we introduce a probabilistic extension. So we use the Leray solutions, which we can construct by compactness argument for every initial condition in L2. And we could connect them to our convex integration solution. Yeah, so basically from 0, we start off by a convex integration solution, and then at some point we no longer continue, but we continue by Leray solution. Yeah, and in the end, to really decide that we have non-uniqueness, we compare the solution constructed through the points 1 and 2 with the usual Leray solution, which starts from the same initial condition. And since for the convex integration solution, the energy is increasing, and for the Leray-Martingale solution, it is decreasing, they are different. Yeah, so actually you also see here that we do not proceed via this Yamada-Watanabe-Engelbert's theorem, which I mentioned a few slides ago. The reason for that is basically the stopping time, that somehow the stopping time bordered us there, and that's why what we did was to construct directly 2 solutions which have different laws. Okay, and so to be more precise, here is the step 1 where we apply convex integration. The important part is that these solutions are really adapted to a given Brownian motion. So they're defined on some given probability space, which is prescribed in advance. And then the statement is the following. Somebody gives us time. This is basically the time where you want non-uniqueness to happen. Yeah, so I can prove non-uniqueness for arbitrary time interval, arbitrary short in particular. I don't have to wait for uniqueness to happen. It happens immediately. Then I have a constant k and I have another constant kappa. Basically, k tells me how much do I want my energy to increase, and kappa tells me with how big probability I want all this to happen. And then there exists some parameter gamma, which is a regularity exponent. It will be regularity of my solutions, and it is small. Yeah, depending on all these other parameters, it is a small exponent, but it's positive. And there exists a strictly positive stopping time tau, so that the probability that tau is bigger than my prescribed time is bigger than kappa. Yeah, so the probability that these solutions are bad at time capital T could be arbitrarily large. And the following holds true. There exists an adapted process U. It has continuous trajectories up to this random time point, takes values in H gamma, all this almost surely, and it is an analytically weak solution. Yeah, so this FT adaptedness, this is what tells me it's a probabilistically strong solution and analytically weak. And now for additive noise, I get this energy inequality. And so if you remember the computation of the energy inequality from one of the first slides, there was the opposite inequality, and also the constant k was not there. And this term is now coming from the noise. So if you try to do the same computation as before with this stochastic equation, you would end up with the opposite inequality here, and you wouldn't have these constants. And actually, you would have also some expectations flying around. So what we do here, we postulate the opposite of what is physical. For the linear multiplicative noise, it looks a little bit different just because the noise is different. And so there we postulate again the opposite of what should be there for Leray solutions. And you see that on this set, where my stopping time is beyond the time capital T, these inequalities hold true. And this is how I quantify that my solution behaves badly at time capital T. Yeah, so this is the first step. The probabilistic extension is then rather technical. I mean, it's technical. So somehow let me try to explain to you what is the main point and what are the difficulties. So for the convex integration, we have solutions which exist on a given probability space. So that's nice. On the other hand, they exist only up to this funny stopping time, which is not nice. And so when you ask yourself how to extend them to zero infinity, well, first you may want to think, well, I start somewhere and then wherever I end, I take this as my new initial condition and I do convex integration again. Yeah, that does not seem to work here because the convex integration that we use does not solve the Cauchy problem. Yeah, it's somehow, it's not that I prescribe initial condition and then I can do convex integration there. Although there are now other results in the literature, but yeah, when we were writing this paper, this is how we had it there. So it did not solve the Cauchy problem. And so somehow the initial condition came implicitly from the construction. And that's why I cannot continue convex integration solution by another convex integration solution. On the other hand, we have Leray solutions. Here, martingale stands just for probabilistically weak solutions, meaning they're obtained by compactness. They are not adapted to the Brownian motion. They're not also, they do not exist on every probability space. That's always the drawback of a compactness argument in the stochastic setting. But then they have one very nice advantage, namely, they can be constructed for every initial condition in L2 divergence free. Yeah, so for every initial condition, but not on a given probability space. Okay, and so our idea was really to look at their push forward measures, to look at the induced probability laws, and basically this way move the convex integration solutions and the Leray solutions to the same probability space, which is then the canonical path space. And there were many technical difficulties related to the stopping time, because somehow the stopping time is not a stopping time with the filtration you would like it to be, but I think I should not go really too much into details here. At some point, there is also a measurable selection argument. Yeah, but somehow roughly speaking, really the idea is to take the law of a convex integration solution and then by this probabilistic extension, connect it to a law of such a Leray martingale solution. And this way we get a probability law which solves the system on zero infinity. Okay, and then finally, this brings me to the final statement. So for every prescribed capital T positive, so this is what I mentioned, that we don't have to wait for non-uniqueness to happen. For an arbitrarily small time, we can prove non-uniqueness. So then non-uniqueness in law holds on zero capital T. Yeah, and basically now I think it's pretty clear what to do, because if you have the previous theorem, you just choose your parameters k and kappa. Somehow you have many options to do that, and you get a solution with which at time t behaves badly, and you compare it to the Leray solution, which behaves well with respect to the energy inequality. Yeah, and so you compare them, and since one has the wrong energy inequality, the other one has the correct one. That's why they are different. And this is how we prove non-uniqueness in law. And with this, I would like to thank you for your attention.
Thank you very much, Martina, for your wonderful talk. Like really, really nice. Excellent results. Just want to ask everybody if you have any questions or comments, you can unmute yourselves.